C# and AI Masterclass by Edgar Milvis Volume 9, Chapter 2. Let's discuss Chapter 2, Understanding Model Formats, ONNX versus GGUF. Now, let's talk about theoretical foundations. In the realm of local AI inference, the model file format is not merely a container, it is the blueprint, the engine, and the transmission protocol all in one. It dictates how efficiently a model can be loaded into memory, how effectively it can be accelerated by specialized hardware, like GPUs via CUDA or DirectML, and how seamlessly it integrates into a managed environment like .NET. To master local inference in C#, one must first master the formats that make it possible. Let's discuss the dichotomy of formats, ONNX versus GGUF. Imagine you are an architect designing a universal library. You have two primary options for storing your books, models 1. ONNX, Open Neural Network Exchange. This is the universal library standard. It defines a strict, standardized layout for every book. Every chapter, layer, paragraph, operation, and word, parameter, has a specific location and format. This standardization allows any librarian, hardware accelerator like NVIDIA, Intel, or AMD, to instantly understand and index the book without needing to learn a new language. However, because the standard is rigid and verbose, the books are physically heavy and require a specific, sometimes cumbersome, shelving system to read efficiently. 2. GGUF, GPT-generated unified format. This is the compact digital archive. It is designed specifically for speed and efficiency in a digital reader. It bundles the text, weights, with a detailed metadata index at the start of the file. This allows the reader, CPU/RAM, to memory map the file, essentially creating a direct pointer to the data on the disk without loading the entire book into the device's limited RAM. It is highly specialized for reading, inference, but lacks the universal hardware acceleration support of ONNX. In the .NET ecosystem, this distinction is critical. C# developers often require the raw performance of hardware acceleration for production-scale applications, ONNX, while also valuing the simplicity and low memory footprint for desktop or edge applications, GGUF. Now, let's explore deep dive, ONNX, Open Neural Network Exchange. ONNX is an open-source format built to represent machine learning models. It acts as an intermediary bridge between training frameworks, like PyTorch or TensorFlow, and inference engines. Let's discuss the computational graph, the universal blueprint. At its core, an ONNX model is a computational graph. It does not contain the logic of how to calculate a matrix multiplication, rather, it contains the structure of the operations and the parameters, weights, required. Think of an ONNX model as a factory assembly line diagram. Nodes, these are the machines on the line, e.g., convolution machine, activation machine. Edges, these are the conveyor belts carrying raw materials, tensors, between machines. Initializers, these are the stored raw materials, weights, preloaded into the machines. When you load an ONNX model in C#, you are not loading executable code, you are loading a declarative description of a mathematical process. The .NET runtime, specifically the ONNX runtime, reads this diagram and maps it to the most efficient execution provider available on the hardware. Let's discuss why ONNX is crucial for .NET AI applications. In Book 8, we discussed the iChat client interface, which allowed us to swap between OpenAI client and Allama client via dependency injection. ONNX takes this abstraction to the hardware level. ONNX runtime for .NET, Microsoft.ml.onx runtime, provides a unified API to execute models across diverse hardware. CPU execution provider, CPU EP uses standard CPU instructions. Slow but universally available. CUDA execution provider, NVIDIA maps graph nodes directly to CUDA kernels. This is essential for LLMs, as the massive matrix multiplications are parallelized on the GPU. DirectML, Windows. The standard for GPU acceleration on Windows, supporting AMD, Intel, and NVIDIA cards. The C# connection, in a C# application, you don't write the math for the Llama model. You instantiate an inference session. We begin by importing necessary namespaces. Microsoft.ml.onx runtime is the core library for interacting with ONNX models, providing the inference session class which is our primary entry point. Microsoft.ml.onx runtime, tensors provide specialized tensor types like dense tensor for efficient data handling, crucial for numerical computations. Notice how we instantiate an inference session at line 5, pointing it to our model.onx file. This is where the ONNX runtime loads the pre-trained neural network model. The second argument, session options. Make session option with CUDA provider, is a critical architectural choice. It tells ONNX runtime to leverage the NVIDIA CUDA framework for GPU acceleration. This decision dramatically impacts performance, as deep learning models benefit immensely from the parallel processing capabilities of GPUs. Without this, the inference would fall back to the CPU, which is significantly slower for complex models, especially LLMs. This choice is vital for achieving real-time or near real-time inference speeds, which is often a requirement for edge AI applications. Here, we prepare the input data for our ONNX model. Think of these inputs as the raw material we feed into our machine learning pipeline. At line 9, we create a dense tensor float. This is a multidimensional array optimized for numerical operations. The new float, /*token IDs */ placeholder would typically contain the numerical representations of our input text, such as token IDs generated by a tokenizer. The 512 array defines the shape of our tensor, 1 for the batch size, meaning we are processing one sequence at a time, and 512 for the sequence length, the maximum number of tokens our model can handle. This shape is crucial and must match the input shape expected by the ONNX model. If there's a mismatch, the runtime will throw an error. At line 10, we wrap this tensor in a named-onks value. This is how ONNX runtime associates our data with a specific input node in the ONNX graph, identified by the name input_IDs. This naming convention must precisely match the input names defined within the ONNX model itself. Incorrect naming would prevent the runtime from correctly mapping the input data to the model's expected inputs, leading to runtime errors. Finally, at line 13, we execute the model inference. The session, run, inputs, call is where the magic happens. The ONNX runtime takes our prepared inputs, feeds them into the loaded ONNX model, and performs all the computations defined in the model's graph. Because we specified the CUDA provider earlier, this execution will primarily happen on the GPU, leveraging its parallel processing power. The using var results equals syntax ensures that the results object, which contains the model's outputs, is properly disposed of after use, releasing any underlying unmanaged resources. This is a best practice in C# to prevent memory leaks. The results object will contain one or more named-onks value instances, each representing an output tensor from the model. We would then extract and process these output tensors to get our model's predictions, such as the probability distribution over the next token in an LLM. Why this matters: if you are building a high-throughput API, e.g., a chatbot backend, you cannot rely on CPU inference. ONNX allows you to leverage the massive parallelism of your GPU without writing a single line of CUDA code. The format separates the model definition from the execution logic, allowing the .NET runtime to optimize the graph for the specific hardware at runtime. Let's discuss the static graph limitation. ONNX is a static graph format. Once the model is exported, the structure, number of layers, connections, is fixed. Analogy: ONNX is like a printed circuit board. You can send different electrical signals through it, but you cannot reroute the copper traces without manufacturing a new board. Implication for LLMs: this works perfectly for standard transformer models. However, if your model requires dynamic control flow, e.g., an if statement inside the model that changes the architecture based on input, ONNX struggles. It requires unrolling loops, which increases file size. Moving on to deep dive, GGUF, GPT-generated unified format. GGUF was created by the community, specifically for the llama.cpp project, to solve the memory and loading inefficiencies of older formats like GGML. It is designed specifically for inference, not training. Now, let's talk about the memory mapping marvel. The defining feature of GGUF is its ability to be memory mapped. Imagine you need to read a specific chapter in a 500-page book stored on a hard drive. Traditional loading, like ONNX/PyTorch, you must pick up the entire book, 500 pages, carry it to your desk, RAM, and open it. This takes time and requires a large desk. Memory mapping, GGUF: you place the book on the desk but leave it closed. You create a direct index, chapter 5 starts at byte 40,000. When you need chapter 5, you don't carry the whole book, you simply look at that specific location on the disk. The operating system handles the paging. In C#, while we don't have direct memory mapping APIs for GGUF, as llama.cpp is a C++ library, the concept drives the efficiency. When using a .NET wrapper like llama#, the underlying C++ engine keeps the model weights on disk and only loads the layers currently being processed into the GPU/CPU cache. Now, let's talk about architecture, tensors and metadata. A GGUF file is a binary blob with a simple header. 1. Magic number, identifies the file type. 2. Version, ensures compatibility. 3. Metadata, key value pairs, e.g., tokenizer.ggml.model, llama, block_count, 32. This is crucial for C# applications to know how to instantiate the model context without guessing parameters. 4. Tensor data, the weights, stored in a quantized format. Quantization, the art of compression. GGUF shines in its support for quantization. This is the process of reducing the precision of the weights, e.g., from 16-bit floating point to 4-bit integers. Analogy, high-fidelity audio, FLAC, versus MP3. The MP3 removes data the human ear, or the neural network, is unlikely to notice, drastically reducing file size with minimal perceptual loss. Why it matters for C# desktop apps. A full Llama 3 8B model in 16-bit precision requires 16 GB of VRAM. In 4-bit GGUF, it drops to 4 GB. This allows complex AI features to run on consumer laptops with integrated graphics, a common scenario for C# WPF or MAUI applications. Now, let's talk about the .NET ecosystem, Llama. Since ONNX runtime does not natively support the GGUF format, it requires conversion to ONNX. C# developers rely on libraries like Llama. This library acts as a managed wrapper around the C++ llama.cpp engine. Here, we're importing necessary namespaces from the Llama library. Llama, common typically contains core data structures and utility classes, like modelparams, which we'll use shortly to configure our model. Llama itself provides the main classes for interacting with the LLM, such as LLama model and interactive executor. These imports are crucial because without them, the C# compiler wouldn't know how to resolve the types we're about to use, effectively preventing us from loading and running our language model. We are now defining the modelparams object, which is absolutely critical for configuring how our GGUF model will be loaded and executed. Think of this as the blueprint for our model's operational environment. The most important parameter here is the path to our GGUF model file, models/llama 3-8b instruct.q4_k_m.guf. This tells the Llama library exactly where to find the pre-trained weights and architecture. The GPU layer count equals 20 is a performance-critical setting. It instructs the library to offload 20 layers of the neural network to the GPU. This is a form of partial offloading or hybrid execution. By leveraging the GPU for computationally intensive layers, we significantly speed up inference, especially for larger models, while potentially keeping less memory-intensive layers on the CPU. The alternative would be running entirely on the CPU, which would be much slower, or entirely on the GPU, which might exceed GPU memory for very large models or smaller GPUs. This decision directly impacts inference speed and memory footprint. This line is where the magic of loading the LLM actually happens. We're using llama_model.load_from_guf parameters to instantiate our language model. The using var model syntax is important. It ensures that the Llama model instance, which likely holds significant unmanaged resources, like memory-mapped model weights, will be properly disposed of when it goes out of scope. The load_from_guf method specifically handles the GGUF, GPT-generated unified format, model format, which is very popular for local LLM inference due to its efficiency and flexibility in supporting various quantization levels. The model is typically loaded using memory mapping techniques. This means the model file isn't fully read into RAM but rather parts of it are mapped directly from the disk into virtual memory. This is a huge advantage for very large models, as it allows us to load models that are larger than our physical RAM, relying on the operating system's virtual memory management. Without memory mapping, loading a multi-gigabyte model could easily exhaust available RAM, leading to crashes or extremely slow performance due to excessive swapping. Here, we're creating an interactive executor instance, passing our loaded model to its constructor. The interactive executor is a crucial component that abstracts away the complexities of interacting with the underlying C++ inference engine. Think of it as the brain that orchestrates the conversation with our LLM. While the Llama model loads the weights, the interactive executor provides the high-level interface for sending prompts and receiving responses in a conversational manner. This separation of concerns is good architectural practice. One component, Llama model, handles the low-level model loading and configuration, while another, interactive executor, manages the inference flow and user interaction. This design makes the system more modular and easier to maintain. This executor will handle the intricate details of tokenization, feeding tokens to the C++ backend, managing the internal state of the model during a multi-turn conversation, and decoding the output tokens back into human-readable text. The C# connection, interfaces are crucial here. Just as iChat client allowed swapping OpenAI for Llama, a well-designed C# AI application should define an iInference engine interface. Here, we're defining a C# interface named iInference engine. This is a fundamental concept in object-oriented programming, promoting abstraction and loose coupling. By defining this interface, we establish a contract that any class intending to act as an inference engine must adhere to. The core method required is inferasync, which takes a prompt, a string, likely the input text for our language model, and returns a task string. The task string indicates that this operation is asynchronous, which is crucial for I/O bound or computationally intensive tasks like AI inference. Asynchronous programming prevents blocking the main thread, ensuring a responsive application, especially in web services or UI applications. This design allows us to swap out different inference implementations without changing the client code, adhering to the dependency inversion principle. Now, let's look at the ONNX engine class. This class is declared as public and implements our inference engine interface. The comment // implementation for ONNX, high performance, is very telling. ONNX, Open Neural Network Exchange, is an open standard for representing machine learning models. Using ONNX typically implies leveraging highly optimized runtimes, like ONNX runtime, that can utilize specialized hardware, GPUs, NPUs, for significantly faster inference. This implementation would be chosen when high throughput and low latency are paramount, perhaps for a cloud-based API endpoint serving many requests. The internal implementation, though not shown here, would involve loading an ONNX model and executing it using the ONNX runtime API. The /**/ placeholder means the actual implementation details are omitted for brevity, but they would contain the specific logic to load and run an ONNX model. Finally, we have the GGUF engine class, also implementing inference engine. The comment // implementation for GGUF, low memory/edge, highlights its primary use case. GGUF is a file format specifically designed for efficient loading and execution of large language models, LLMs, on consumer hardware, particularly focusing on memory efficiency. This engine would be ideal for edge AI scenarios, where resources, memory, CPU, are limited, such as on embedded devices, single-board computers, or even personal laptops without dedicated high-end GPUs. While it might not achieve the raw speed of a highly optimized ONNX runtime on server-grade hardware, its strength lies in its ability to run models with much less memory footprint and often without specialized acceleration hardware. This architectural choice demonstrates a clear strategy for targeting different deployment environments and performance profiles using the same fundamental interface. This abstraction allows the application to select the engine based on the environment. If the user has an NVIDIA GPU, use ONNX. If they are on a laptop with 8 GB RAM, use GGUF. Moving on to comparative analysis, architectural implications. To visualize the flow of data and the decision-making process in a C# application, consider the following graph. It illustrates how the model format dictates the execution path. The diagram depicts a C# application's workflow where the specific model format acts as a central switchboard, directing the flow of data and determining the subsequent execution path for AI processing. Now, let's explore theoretical foundations. Understanding the formats requires understanding the lifecycle of a model. 1. Training. PyTorch/TensorFlow. The model is trained in Python. The native format is usually a pickle-based serialization, .point or .h5. These are not suitable for C# due to Python dependencies and lack of optimization. 2. Conversion. To ONNX, the Python script calls torch.onx.export. This traces the computation graph and saves it as a .onx file. This file is static and immutable. To GGUF, the model is first converted to an intermediate format, like safetensors, then processed by a quantization tool, like llama.cppsquantize.exe. This tool analyzes the weights, clusters them, and saves them as a binary GGUF file. 3. C# integration, ONNX, the .onx file is dropped into the project. The Microsoft.ml.onx runtime NuGet package is added. The C# code uses inference session. GGUF, the .guf file is dropped in. The llama NuGet package is added. The C# code uses llama-model.load-from-guf. Now, let's talk about why this matters for the .NET developer. In previous chapters, we discussed the abstraction layer, interfaces, to decouple application logic from specific AI providers. The choice between ONNX and GGUF is the physical implementation layer of that abstraction. Interoperability. ONNX is the key to unlocking hardware diversity. Because ONNX is an open standard, a model trained on an AMD GPU in Linux can be run on an Intel CPU in Windows via the same C# code. This is vital for enterprise.NET applications that must run in heterogeneous environments. Latency versus throughput. GGUF is optimized for latency on consumer hardware. It is ideal for interactive desktop applications, chatbots, copilots, where a single user waits for a response. ONNX is optimized for throughput on server hardware. It is ideal for APIs serving hundreds of requests simultaneously, utilizing the massive parallelism of server-grade GPUs. The what-if scenario: what if you deploy an app using GGUF to a server with 4A100 GPUs? You are leaving massive performance on the table. Conversely, what if you deploy an ONNX model to a user's laptop with 4 GB of RAM? The app will crash due to out-of-memory exceptions. Understanding these formats allows you to dynamically select the right engine at runtime or provide different builds for different target audiences. By mastering ONNX and GGUF, you move from being a C# developer who calls AI APIs to an engineer who integrates AI models directly into the .NET runtime, optimizing for the specific hardware constraints of your users. Now, let's explore basic code example. We begin by importing necessary namespaces. Microsoft.ml.onx runtime and Microsoft.ml.onx runtime. Tensors are the core libraries for interacting with ONNX models in .NET. These provide the functionalities to load ONNX models, create inference sessions, handle input, output tensors, and execute the models. The other system namespaces are standard for general-purpose C# programming, such as system, collections, generic for lists and system, link for querying collections, which are useful for managing model inputs and outputs. Here, we're setting the stage for our application. The comments provide a crucial real-world context, explaining that we're building a sentiment analysis feature using a pre-trained ONNX model. This immediately tells us the why behind the code. We're leveraging a machine learning model for a specific task. We are also told that the model is expected to classify text into positive, negative, or neutral, which sets expectations for the model's output and how we'll interpret it. We define our namespace onx inference hello world to logically group our code and prevent naming conflicts, a standard C# practice. Inside, we have our program class, which is the entry point for any console application. The main method is declared as static async task main, string, args. The async task return type is significant. It indicates that our main method can perform asynchronous operations, which is often crucial for I/O bound tasks like loading models or running inference, especially in more complex applications where responsiveness is key. We start by printing a welcoming message to the console, making the application user-friendly. At this point, we define model path, a string variable holding the filename of our ONNX model. This is a critical first step because without the model, we cannot perform any inference. The comment clarifies that in a real-world scenario, this model might be downloaded or bundled, but for this example, we assume it's present in the execution directory. This decision simplifies the setup for a hello world example but implies that in production, robust model deployment strategies, e.g., embedding as a resource, fetching from blob storage, would be necessary. We also note the model's expected input, string, and output, logits for 3 classes, which are vital pieces of information for subsequent preprocessing and post-processing steps. We introduce a try-catch block, which is a fundamental error handling mechanism in C#. This is a best practice, especially when dealing with external resources like files, our ONNX model, or complex operations that might fail, like model inference. Inside the try block, we define input text, the string we want to analyze. This is our raw input data, representing a user's comment or a piece of text from a document. This text will undergo preprocessing to be understood by our ONNX model. Here, we delve into the crucial step of preprocessing. Machine learning models, especially deep learning ones, don't directly understand raw text. They require numerical inputs. The comment explains that real-world applications use tokenizers to convert text into numerical IDs. Since this is a hello world example, we simulate this process. We declare a long token IDs of a fixed size, 128, representing a batch size of 1 and a sequence length of 128. This shape, 128, is a common input format for many transformer-based models like BERT. We then manually assign some simulated tokens to represent words and special tokens, like 1014, CLS, and 1024, SEP, in BERT-like models. This simulation is a pedagogical choice. It allows us to focus on the ONNX runtime integration without getting bogged down in the complexities of a full tokenizer implementation, which would typically involve vocabulary lookups and subword tokenization. Now we move to creating the inference session with ONNX runtime. The using var session equals syntax is a C# feature that ensures the inference session object, which consumes system resources, is properly disposed of once it goes out of scope. This is vital for resource management, preventing memory leaks, especially in long-running applications or services. We create session options and set log severity level to ort_log_level_warning. This means ONNX runtime will only log warnings or more severe messages, reducing console clutter and focusing on potential issues rather than verbose informational messages. This is a good practice for production deployments where excessive logging can impact performance and storage. At line 55, we instantiate inference session. This is the core object that loads the ONNX model from the specified model path into memory. This step also performs initial validation of the model structure. It's important to understand that loading the model does not run any inference yet, it merely prepares the model for execution. The session options configured earlier are passed here, allowing us to customize aspects like logging verbosity or execution providers. This design separates model loading and configuration from the actual inference execution, providing flexibility and control. With the session ready, we now prepare the inputs for the model. ONNX runtime expects inputs as a list named donks value. The name donks value is crucial because it links our input data to the specific input names defined within the ONNX model itself, e.g., input_IDs. If this name doesn't match exactly, the inference will fail. We wrap our token IDs array, which contains the numerical representation of our text, into a dense tensor long. A dense tensor is ONNX runtime's primary way to represent multidimensional arrays of numerical data, which are the fundamental data structures for neural networks. The constructor new128 defines the tensor's shape, a batch size of 1, meaning we are processing one sentence at a time, and a sequence length of 128 tokens. This explicit shape declaration is vital for the model to correctly interpret the input data. Before running inference, we print out the input text and the shape of the input tensor. This is excellent for debugging and verifying that our pre-processing steps have correctly prepared the data. Then, at line 73, we execute session.runAsync, inputs. This is where the magic happens. The ONNX runtime takes our prepared inputs, feeds them through the loaded ONNX model's computational graph, and performs the actual predictions. The async keyword is important here, as runAsync allows the operation to be non-blocking. While in a simple console app, this might not seem critical, in a GUI application or a web service, it would prevent the UI from freezing or the server from becoming unresponsive during potentially long inference operations. The using var results equals ensures that the iDisposable results object is correctly managed. After inference, we enter the post-processing phase. The model's raw output, often called logits, is typically a tensor of floating point numbers representing unnormalized scores for each class. At line 79, we extract this output. We assume the output name is logits, which is a common convention for classification models. We retrieve the first, and likely only, output from the results collection and cast it to a dense tensor float. This output tensor now holds our model's predictions in a numerical format. Understanding the structure and meaning of this output tensor is crucial for correctly interpreting the model's decision. Here, we interpret the raw logits from the model. While a full softmax function would convert these logits into probabilities, summing to 1, for simplicity and to find the most likely class, we perform an argmax operation. This means we iterate through the output scores and find the index corresponding to the highest score. This index directly maps to our sentiment classes, 0 for negative, 1 for neutral, and 2 for positive. This approach is efficient for determining the predicted class without needing to calculate full probabilities, which would involve exponentiation and division, adding computational overhead if only the most likely class is needed. We initialize predicted class to 0 and max score with the first element's value, then iterate to find the actual maximum. Finally, we map the predicted class index to a human-readable sentiment label using a C# switch expression. This makes the model's output understandable to the user. The _=unknown case is a good defensive programming practice, handling any unexpected predicted class values, although in a well-defined 3-class model, it should ideally not be hit. We then print a summary of the inference results, the raw logits, useful for debugging and understanding the model's confidence, the predicted class index, and the detected sentiment. This provides a clear and concise output for the user, demonstrating the end-to-end functionality of our sentiment analysis feature. This catch block specifically handles file not found exception. This is a common and predictable error when dealing with file paths, especially for external resources like our ONNX model. By catching it explicitly, we can provide a user-friendly and actionable error message, guiding the user to check the model's presence and path. This is much better than a generic exception, as it helps diagnose the problem quickly. We also use console.foreground color to highlight the error message in red, improving visibility and user experience. This final catch block is a general exception handler. It catches any other exception that might occur during the program's execution that wasn't specifically handled by the file not found exception block. This is a crucial safety net for robust applications. While specific exception handling is preferred, a general catch ensures that the program doesn't crash unexpectedly but instead reports an error gracefully. Again, we use color coding to make the error message stand out, providing a consistent user experience for error reporting. By scanning this qrcode you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. This lesson is excerpted from Volume 9, Chapter 2 of the C# and AI Masterclass ebook series and from the volume Edge AI and Local Inference. Running LLMs, Llama/Phi, locally with C# and ONNX. You can find all source code here, https://github.com/edgarmilvis/C# programming series. The ebook includes 20 chapters, each one with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. Thank you for your attention. I look forward to seeing you in the next lesson.